Because if you think about it, whatever I said here, the velocity field of particle 1 is going to make particle 2 move, right? Do you agree with that idea? So what is, let's put a 0 here, let me just make sure. So the velocity of sphere 1 is Phi e by 6 pi mu a1. Velocity of sphere 2 is F2 e by 6 pi mu a2, right? Focus on particle 1. If I say that the disturbance velocity, so I will put a, let's put a hat here. The disturbance velocity of sphere 1 due to this isolated motion, what is that? What is the disturbance velocity created by sphere 1 if it was moving in isolation? See, these are isolated pictures, right? Do you agree? U10 is the isolation picture for sphere 1, so it translates with a certain velocity. U20 is the translational velocity of sphere 2, again in isolation. U1 tilde 0 is the velocity field created by the translating sphere when it is in isolation. So what is that velocity field?
In an isolation, will it have its own disturbance field?
Obviously, yes. It should, right? If there is a sphere that is falling, this entire red line is the velocity field that is generated. So when you move, you are not moving in vacuum, you are moving in the fluid, right? So when there is a sphere that is falling with a certain velocity, it is going to create a disturbance. So what is a disturbance?
You are asking at the surface.
Everywhere. Maybe it has been some time, which is why you are forgetting it. And then the third order term. Right? This is the velocity field generated by a translating sphere. Instead of writing it in terms of the translational velocity, I wrote it in terms of the force. Right? You are balancing the drag force with the external force. So I am substituted for the translational velocity. This is exactly how we get the Stokes line. We push A to 0 and then we get the first term. So this is the disturbance field which is denoted by those red lines. Now what should be the velocity of sphere 2 in this velocity field? So this distance x, how is it measured? It is measured with respect to sphere 1 center, right? So my question now is, what would be the velocity of sphere 2 in this particular velocity field, or due to this disturbance velocity field? So let me write this: disturbance velocity field due to translation of sphere 1. So what should be the velocity with which sphere 2 now should move? This is where you go back to Faxén's relation. What does Faxén's relation tell us? that the total force acting on a sphere is, what is it? 6 pi mu A2. If it is translating with some velocity, so if there is a sphere which is translating with some velocity u2 in a flow field that is u infinity, then what is the drag force on the sphere?
U2 minus U.
Minus sign u2 minus u infinity at the center of sphere, right? So, if I say this is at some position x2, and then what is the next thing? Which is minus a square by 6 del square u infinity at the center of that particular sphere. Do you remember this? The drag force on a sphere that is translating with a velocity u2 in some background ambient flow u infinity, which is a Stokes flow. That is important. U infinity should be a Stokes flow. So, if it is in some background ambient Stokes flow, then the drag force is this. Now, for sphere 2, what is F? F2, that does not change, right? Or rather F2, which becomes minus F2E. So, what is F2E? F2E is minus 6 pi mu A2 U2 0, right, is equal to minus 6 pi mu A2 U2 minus U infinity is now the disturbance of sphere 1 evaluated at the center of sphere 2, which is at a separation vector of r from sphere 1, minus a square by 6 del square u infinity, which becomes del square u1 0 at r. Is that okay? So, what you are saying right now is u2, the translational velocity of sphere 2 is u2 0 plus u1 of 0 r plus a square by 6 del square u1 of 0 r. This is the background u infinity as seen by sphere 2 that is generated by sphere 1. So, this part you can now write as u2 1. That is the correction to sphere 2's velocity. See, the force acting on sphere 2 does not change. That is Fe, F2E, that is what it remains. We are not changing the force on the sphere, which means the drag force does not change. So, I as a sphere 2, I need to move in a slightly different way such that in this background flow the drag still remains the same. When there was no background flow, I was moving with a velocity u2 of 0. But now because there is some background velocity, I cannot change the drag has to be the same because the drag is balanced by the external force. The external force is not changing, the weight of the particle is not changing. So, because the drag is held fixed, I need to alter my motion when I am in the presence of some background flow. That is the core idea. So, now the velocity gets corrected by a term that is the disturbance of sphere 1 evaluated at the center of sphere 2, and there is a Laplacian term. Do all of you get this point? Now, how does this decay with r? You have it here, right? This has a 1 over r term and then 1 over r cube term. What about the Laplacian? How does the Laplacian decay? So it will have once again a order 1 over r cube term, right? When Laplacian means taking derivative twice. So when you take a derivative twice of a 1 over r, you are going to get a 1 over r cube. And then what's the next term? Okay. Now this is where what we are going to say is, when I am doing a reflection calculation, I will just focus on the leading order 1 over r term, which means u2 is going to be u2 0 plus u2 1, where u2 0 is f1 e by 6 pi mu a1 and u2 1 is, sorry, this is f2. u2 0 is f2 e by 6 pi mu a2 and u2 1 is the order 1 over term of u1 0. The order 1 over term is f1 e by 8 pi mu dotted with delta by r plus xx by r cube. So I have ignored all terms that are higher order than 1 over r. I have only kept this. Similarly, if you do this exercise for u1, this is going to be u1 of 0 and then u1 of 1, the first correction that you are going to get. So this is once again going to be f1 e by 6 pi mu a1 and then f2 e 8 pi mu dotted with delta by r plus xx by r cube. So with this exercise, what we have now is that u1 u2 is equal to delta by 6 pi mu a1 delta by 6 pi mu a2. These are the diagonal entries of the mobility tensors. But then you have an additional term here, which is delta by r plus xx by r cube with a 1 by 8 pi mu. So you have obtained the effect of interaction here. So I have just stopped it at the first level of interaction, because now you can also see there are many things which we have not done here. For instance, this disturbance is going to create a vorticity. The disturbance created, we never discuss about vorticity, but the disturbance that is created by that translating particle has an associated vorticity. So sphere 2, which is in the vorticity field of sphere 1, in order for it to be torque free, because there is no external torque, it has to spin. So in isolation it does not spin, and a translating sphere in isolation does not spin, but a sphere, when it interacts with another sphere, it has to spin. But that spin is not going to create a drag on the particle, so it will not change the translational motion of the sphere, but you will get a spin. So if you have two spheres which are falling, if they are infinitely far apart, they will move with settling velocity given by Stokes terminal velocity and they do not spin. But when you bring them closer, their settling velocity is going to change, but they are also going to have a spin that they will pick up. So, here we did not work out the spin, but that is something which will happen. So, now with this, if I try to find what is the relative velocity, the relative velocity is going to be delta 6 pi mu a1 dot f1e plus 1 by 8 pi mu delta by r plus xx by r cube dot f2e minus delta by 6 pi mu a2 dot f2e minus 1 by 8 pi mu delta by r plus xx by r cube dot f1e. So, if I write this out, I have delta, so I will take the 6 pi mu outside. So, I will have f1e by a1 minus f2e by a2 right, and then I have 1 by 8 pi mu delta by r xx by r cube dot f2e minus f1e. Is this okay? Did we get all right? So, delta dot f1 is f1, right. What happens when the two spheres are identical? So, f1 is same as f2, a1 is same as a2. So, what is your conclusion? Relative velocity is 0. Does this remind you something that you did earlier? You used a reversibility argument without doing any calculation. The reversibility and symmetry argument to say that two identical spheres falling under gravity, they will not have any relative motion. You can argue that using reversibility and symmetry arguments. Now, you see this using the first reflection. You can go higher orders in reflection and this will continue to be true. So, when there are two identical spheres, the relative velocity is 0. They do not approach each other, they do not drift away from each other. And this you can see what we argued using symmetry and the fundamental reversibility point of Stokes flow is actually applicable or can be derived out from first reflection. For a1 equal to a2, what is the velocity of the center of mass? Obviously, u1 is equal to u2. So, I can take half of this, that is the velocity with which its sphere is going to move, right, because u1 is equal to u2. So, what is it? Delta dot this one. So, it is f1 plus f2, they are identical. So, let me first write it with that, and 6 pi mu, this one is a1 inverse, a2 inverse, and then 1 by 8 pi mu delta by r plus xx by r cube dot f2 e plus f1 e, right. There is a factor of half everywhere. I am trying to find out what is the velocity of a single sphere, which is u. So, what will it be here? F1, so it is just the force acting, I will just write it as F by 6 pi mu A plus 1 by 8 pi mu delta by r plus xx by r cube dot f. This is the velocity with which it is going to fall. Now you can answer something. What happens in these two configurations? Yeah.
So for the previous case, if A1 is equal to A2, how like F2 is equal to F1 is equal
Because we are saying F1, F2 is the weight of the object. In this problem, we are considering the external force to be the weight of the object. It's a sedimenting problem. In this particular case, the external force is the weight. So we are, which is why if they are identical in size and we are also considering the density to be identical, so F1 is equal to F2.
So if it was not a sedimenting problem or an external force was there, then this would be
Yeah, so even if it was a sedimenting problem, but you had two spheres identical in size, but one was a water droplet, the other was a like some metal particle, they will have different density. So then F1 and F2 will not be the same even though A1 is equal to A2. And obviously you can do many other scenarios. So what is the difference between the two cases? Here F is perpendicular to R because this is the separation vector. Here F is parallel to R, right. So when you do this in the perpendicular configuration, you will have F by 6 pi mu A. So what is the dot product of F with, I mean this is x actually, yeah. So x, what is that term? 0, right. So you are going to get F divided by 8 pi mu R, which means this is F by 6 pi mu A into 1 plus A by R. So what do you conclude here? As it gets closer, what happens? That is 8, right, thank you. So that is going to be 3 by 4. Right. So what do you conclude? As it gets closer, as R gets smaller and smaller, is going to settle faster, right. It is basically falling faster. What about here? U parallel. This is F by 6 pi mu A by 8 pi mu. F dot x is F times R, right, for this configuration. So this becomes F by R, and then I am going to get again F by R, right. F dot x is F times R, and again F dot, I mean multiplied with that x term, this x can be written as x hat. Okay. So well, this is F times R, not F vector. So then this becomes F by 6 pi mu A 1 plus (3 by 2) A by R. So U perpendicular by U isolated is 1 plus 3A by 4R. U perpendicular by U isolated is 1 plus 3A by 2R. If you were to consider R equals to A, even though that is not the correct thing to do, because this is strictly applicable when R is much greater than A. But if you were to consider R equals to A, just by being a little careless, if you do this, what do you get? R equals to not A, R equals to 2A. you are looking at, r is the center to center distance, right? So that will be r equal to 2a when they are touching. So this is like when they are forming a doublet. So r equals to 2a means 1 plus 3 by 8 and then 1 plus 3 by 4. So this is the ratio of u perpendicular to u parallel is 11 by 8, 7 by 4, which is 11 by 14. What was it in slender body theory? When you have a fiber moving u perpendicular by u parallel, it was approximately around a factor of half, right. So the exercise here, what I am trying to say is that with this kind of an approach, you are finding that motion of two spheres as they get close, this is like a dumbbell, which in many ways the number is numerically close to what you also got from slender body theory. But you can stop here without going all the way far to r equals to a, and you can see that the spheres are going to obviously settle faster once they are aligned one above the other than ones when they are aligned parallel to or when they are aligned in the horizontal plane. So there will be no relative motion, but there would be a faster settling behavior due to the interaction of the two spheres. So you will not see them go closer, you will not see them go away, but you will see them fall with a velocity that is much higher than what an isolated sphere would fall with. Okay, fine. So with this I will end this discussion today. We will see a little bit more on the discussion on reflection, and then we will go to the other limit, which is when we bring them very close.
Sir,
Yeah.
how does this method satisfy the boundary condition?
It doesn't. That's a good point. It is satisfying it approximately. The satisfaction of the boundary condition is obviously becomes better and better as they get further and further away. See, for instance, this this bit, this is exact if there was no sphere 1. If you say there is a velocity field from sphere 1, then the boundary condition satisfied on sphere 2 will give you exactly this. But then the motion of sphere 2 in the velocity field of sphere 1 is going to not satisfy the boundary condition on sphere 1. So which is the reason that you need to do this kind of a reflection exercise. And so when you do this exercise at the every order, the terms that you are generating are going to be higher powers of 1 over r. That is the justification that you make. That the terms that you are ignoring are terms that are 1 over r square, 1 over r cube, 1 over r to the power 4, 1 over r to the power 5. So as the separation gets larger, this approximation becomes better. So the claim is never that this approximation is a great approximation irrespective of the separation. No. This is just to show that how you tackle interaction and how can you get a result that is due to interaction. Because otherwise it's impossible to do something like this. That how do you find the average settling velocity of two identical spheres? How do you solve that problem even? There's no other hope, right? You have to do it fully numerically. But here, using the idea of Faxén, using the idea of mobility tensors, you are able to at least get an approximation as an answer. And it doesn't do that bad. I mean, if possible, I'll show you the numerical result of the actual numerical solution of u perpendicular by u0 or u parallel by u0. And it agrees quite well with these simple expressions that we have here. 1 plus 3a by 4r or 1 plus 3a by 2r.